Ready to go? So we have the second book today about Khazhgali Kozhasov from in Germany, who is now a postdoc in Germany. And the title is here, joint book with Bernard Nasser. Please.
Okay, thanks a lot for the opportunity to present our work here. So I will report on a joint work with Jean Bernard that we submitted to our guide. Okay, so the purpose of the talk is to tell you about some properties of volumes of sublevel sets of homogeneous polynomials that have been studied by Jean Bernard and some other authors. So I will give you an overview of my talk. So there will be three parts. So first I will explain one theoretical result that is complete monotonicity of the volume of the sublevel set of a positive definite form. Then I will talk about forms with sublevel sets have finite volume. And then I will tell a little bit about Gaussian-like exponential densities and inspired by sums of squares. Okay. So I will fix a framework. So by HN, I will denote the space of real and n-ary forms of degree D. By CDN, I will denote the cone of positive definite forms. So that is the forms that take only positive values on Rn without the origin. And I will take the non-negative cone, which is just the closure of this open convex cone C. And then very important will be to fix an inner product, which appears in many talks in this workshop. That is a Behaviour inner product. So if you have two forms written in the basis of monomials, and this is the formula that defines this scalar product. Sometimes it's also called Fisher or a polar product. The dual cone to C is sometimes called the moment cone. So it consists, if you dualize your space of forms by this linear scalar product, then it can be identified with the convex hull of the image of this Veronese map, that is the convex hull of the powers of these powers of linear forms. And finally, by sigma dn, I will just denote the cone of sums of squares. Okay. Okay, now what do I mean by sublevel set of a negative form? So if I pick any form G, then its sublevel set will be just a set of all those x where G takes value at most 1. Okay. And first of all, if we want to study the Lebesgue volume of such a set, then first observation that if we want to have finite Lebesgue volume, then necessarily it's very easy to see the form has to be non-negative. Okay, that's the first observation. Because otherwise, if form G takes negative values, then you can put inside the sublevel set infinite volumes. So it's very easy to see. Okay. Moreover, if you take a positive definite form, then the sublevel set will be compact, okay, and hence its Lebesgue volume will be finite. So that is why we want to study the following function that we will sometimes refer to as the volume function. So we associate to every positive definite form G, it's the volume of its sublevel set, which also can be computed as integral of this exponential of minus G over R to the n up to this constant gamma function. Okay? So, and in 2016, Jean Bernard, among other properties, established that this function is strictly convex on the cone C. And we used this property in 2020 with Jean Bernard to prove that the power of the sums of squares of the variables that I denote by BDN is the unique minimum of the volume function among all forms that have fixed Behaviour norm. Okay, so you consider compact domain of forms of non-negative forms that have fixed Behaviour norm, and then if you try to minimize the volume function of the sublevel set among all such forms, then the power of the this quadratic will be the unique minimizer. Okay. That simply follows from invariance of the Behaviour form of the Lebesgue volume and strict convexity of this function. Okay, and now we would like to go further beyond convexity and talk about slightly stricter notion of convexity that is not maybe as popular as convexity, but still appears sometimes in different contexts. So I will call a smooth function on any open convex cone C completely monotone if the following condition happens. If I take the k directional derivatives and of my function f and multiply by this sign -1 to the k, then this function has to be non-negative on the cone C. Okay. Here, h1, hk have to come from the cone itself. Okay, they have to, the directions have to point in the cone, and k can be arbitrary natural number. Okay, so this is infinite sequence of conditions on the function f, and so plugging in any h1, hk, and taking any k, you obtain a lot of non-negative inequalities. Okay. And by a directional derivative, I just mean dot product with a gradient. So if I take any direction h. And there is a beautiful characterization of such functions that is due to Bernstein in the univariate case, and then Choquet did a complete picture for the codes. Okay, a function f is a completely monotone if and only if there exists a unique Borel measure mu that is supported on the dual cone to C, so that f admits the following integral representation. So it's a Laplace transform of the measure mu, where Laplace transform literally means this. We take integral of exponential of dot product of theta g and integrate over against d mu theta. Okay? And as a consequence, any CM function, any completely monotone function, first of all, is non-negative, minus gradient of your function takes values in the dual cone, and furthermore, the function has to be convex. So complete monotonicity is a much stronger version than convexity or non-negativity. Yeah, please.
So what is the vector G stands for?
So G, this is an abstract setting. G is a vector in your cone C.
Oh, so it's like a point.
Yeah, this is just a point in the cone. So this is an abstract setting. Okay.
And theta are the variables essentially.
Theta is a dual variable. Yes. So but here we consider dot product, so we just dualize everything. Okay. And convexity is easy to see. You can use the integral representation, exploit it to show that if you just bound in a very unique way the integrand of the convex combination, then you can see that Jensen inequality solves. Okay, and convexity. So I think it for at least for like reasonable measure mu, you can even have strict convexity. Probably you can even do it all the time. Okay, and so as I said, as I mentioned in the beginning, so we would like to study this phenomenon for the volume function. And indeed, so what we proved with Jean Bernard is that this function that associates to any positive definite form the volume of its sublevel set is completely monotone on the cone of positive definite forms. And the integral representation is written here. And you can ask, what is the measure? So the measure, of course, we expect to have some Borel measure on the dual cone. And this measure is just push forward of the Lebesgue measure under the Veronese embedding. Okay, so you take the Veronese embedding that already appeared in the definition of the dual of the moment cone, and you push forward the Lebesgue measure into this map. That will be represented measure up to this gamma function. Okay. And the proof is quite elementary, so it follows immediately from this characterization by Choquet. As soon as you take this representation and use a fundamental property that Bombieri enjoys, namely that evaluation of foreign set points correspond to taking inner product with the powers of Wiener points. Okay. That's a one classical property that Bombieri form has, and that's basically all proof, okay, of complete monotonicity. And you can also take the direct definition of complete monotonicity, namely take derivatives, and this is the formula for the any k-fold directional derivative, and you can see that the integrand is non-negative, and believe me, it converges, and so the negativity will follow. Because when you derive exponential of minus g against some h, then it corresponds to multiplication of this exponential by the inner product with h. Okay, so as soon as h comes from the dual cone, So as soon as H comes from the primal cone C and G, so you'll see that this Hj of X is by this formula. It's just taken in a product with point the geometry, so everything remains non-negative. Yes.
So here the measure is supported only on the extreme.
Yeah,
rates.
exactly.
Is that usual or is there something special?
Well, I would say it's rather special, but you will see later that I will mention later that this phenomenon occurs also in other instances. Okay. Yes. So this sometimes happens. Okay. Okay. So and this is not the only instance when complete monotonicity pops up in the context of real algebraic geometry. So there is another series of works that concern hyperbolic polynomials and complete monotonicity. So when you take d + 2 and examine your volume function, in this case, you can easily see that it's proportional to the -1/2 power of the determinant of the quadratic form that defines of the positive definite matrix that defines your quadratic form. Okay? So any degree 2 form can be written in this way, right? X transpose Gx, and then volume function just -1/2 power of the determinant of G. And this function fits into a general picture, namely the following. So in 2014, Scott and Sokol proved that function that sends positive definite matrix to -s/2 power of its determinant is completely monotone if and only if s is either 0, 1, 2, n-2, or greater or equal than n-1. So they characterize completely the set of exponents that you can take to obtain completely monotone power of the determinant of a positive definite matrix. Okay, this is a very non-trivial result. And 2 years later, Mateusz Michalik, Bernstumpfes, Caroline Royal, yes, and Piotr Swernik formulated a conjecture motivated by some algebraic statistic problem. They took any hyperbolic polynomials that is homogeneous with hyperbolicity cone that I denote by CH. And then they conjectured that there exists some value s positive, so that -s power of this polynomial is completely monotone on the hyperbolicity cone. Okay, this conjecture remains open as far as I know up to this day, and it holds for the Follin case list when H admits determinantal power. Okay, so when you can find some power that has determinantal representation, then in this case the conjecture holds essentially by this result of Scott and Sokol. Okay, and second case, it also holds for elementary symmetric polynomial. That is a result in our paper with Berendt and Mateusz. Okay. Yes.
I think this theorem of Scott and Sokol is S is 0, 1, 2, and -2.
Yeah, that's the set of exponents. Finite set.
Oh, okay.
So there is a discrete part of exponents, and then there's like array. Okay.
Is there a identification of the measure?
Yeah, exactly. That's what I promised Greg to tell. So, well, you see that in this case, we know already in the quadratic case that -1/2 power will have the corresponding measure that is supported on the set of rank 1 matrices, right? On the PSD rank 1 matrices. And actually for small s, namely for this discrete range of s, the measure will also be not absolutely continuous with respect to the back measure on the boundary of the cone. And starting from this n-1 and on, it will fill the cone.
So it's the rank structure.
Yes, it's a rank structure. So S will correspond exactly to the rank of so for fixed S among this n-1 values, it will have support on the set of rank S PSD matrices. Okay.
I think somehow it's going to be uniform measure on this.
Well, it's basically so you extend your Veronese map to rank K map, so that sends like K vectors to rectangular matrix transpose times rectangular matrix, right? That parameterizes rank K PSD matrices, and that you push forward your back measure with respect to this map.
Yeah, we're just saying it should have, symmetry properties. So it should be somehow.
So yeah,
Symmetric.
if you act by orthogonal transformation, yeah, it will be yes, it will be invariant. That's true. But yes, when you go to this regime beyond -1, it will fill the cone. Okay. Okay, great. So and by the way, so why you care about hyperbolic polynomials? Because it's a necessary condition to have. So if you want to have that some inverse power of your polynomial h, which does not need to be a priori hyperbolic, then if you want that minus s power of this polynomial is completely monotone, then this polynomial necessarily needs to be hyperbolic. Okay, that's a necessary condition. This is one of the proposition, I think, in Berens and Materis and Caroline and Petter's paper. Okay. So good. And so now I just want to go back to our volume function and explain just SOS version of this. So you can imagine already what's going to happen. So I'm going to take classical representation for sums of squares as given by Gram matrix representation. So I'm going to pick vector of monomials of degree d over 2 and positive definite matrix G or positive semi-definite Gram matrix G. And then if G is positive definite, so then the form, the SOS form will also be positive definite. And that motivates the definition of the SOS volume function that associates any positive definite big real symmetric matrix G, the volume of the sublevel set of the associated SOS forms. And so again, just because this map that sends G to the SOS form is linear, you compose it with completely monotone function, you get a completely monotone function, and the associated integral representation looks similar to the one for the general positive definite case. So here you integrate over the dual of the positive definite form, that is just this decon. And again, your measure is a push forward of the Lebesgue measure under this rank 1 kind of generalized rank 1 map. And again, it is supported on the boundary of the piece decon because of this representation. Okay, so are there any questions after this moment? Okay, so now you can ask the following. So you have that the volume of the sublevel set is infinite as soon as you take not non-negative polynomial. Okay, it's finite on the set of positive definite forms, just because the sublevel set is compact. But the natural question is what happens on the boundary. So when you cross the boundary, does it immediately explode, or something else happens? So for example, so we are interested whether the function, the volume function, is a barrier function for the non-negativity. So barrier is just any function that explodes at the boundary of the cone C. Okay, and Coher in 1957 showed that this so-called characteristic function that is just Laplace transform of the Lebesgue measure on the dual cone, the arbitrary abstract cone C, open convex pointed, let's say, is a barrier function, which is also logarithmically convex. Okay. So this looks similar to the function that we studied, to the volume function, but the only difference is that the represented measure here is a Lebesgue. In our case, it's a single measure supported on the boundary. So this is a barrier function. Our function has a similar form but different behavior. And the natural question, so as I already said, is a volume function that has a similar representation to this phi, so this characteristic function. Is it a barrier for the non-negativity? And the answer, you'll see that it's yes and no. So, for example, in the quadratic case, we know that sublevel set is finite if and only if the form is positive definite, because otherwise you have not pointed cone, you have infinite volume there. And in the binary case, when you have two variables, two homogeneous variables, then non-negative form has finite volume of the sublevel set if and only if the multiplicity of each real zero is at most d half minus 1. So let me just draw how typically sublevel set of a negative form looks like. So if you have some zeros, let's say zeros are the 1, 0 and 0, 1 points. Okay, then this is how more or less sublevel set will look like. So, and if zero gets more singular, so if it has if more derivatives vanish at this real zero, then you can this kind of tentacle will be thicker and thicker. Okay, and then so you can imagine when you, for example, take extreme case x to the power d, just power of linear form, it will be like just a cylinder. Okay. So it will have infinite form. So something should happen. Something should be related to a multiplicity of the zero. Okay, or the vanishing of the non-negative binary form. Okay. So what happens beyond n equals 2? So what happens for a larger number of variables? For this, let me define you a generic form. So I take any non-negative form. I call it generic if every real zero of this form, that is not trivial, is simple. That is, the Hessian at this point has to be of maximal possible rank, that is of corank 1. Corank 1 because of homogeneity. It always has one-dimensional kernel at least. Okay, and so what we prove with Rambert now is that as soon as you take any d even that is larger than 4, then any generic form on the boundary of the non-negativity form will have finitely back volume. Okay, so this is something that you would probably expect, inspired by this two-variate situation, but this is unfortunately not a complete characterization. So this complete characterization, so I will come to this later, but let me, before that, give you some examples of generic forms. So if you take this Robinson form, which is of degree 6 and 3 homogeneous variables, then it has 10, projectively 10 real zeros, and all of these real zeros are simple. So hence this form is generic, and hence it will have finite volume. Another classical example is Motzkin form. And as we figured out on Monday, it's not generic because it has only 4 zeros that are simple and 2 zeros that are not simple, that have high multiplicity. But still, in this case, the sublevel set of this Motzkin form will be will have finitely back volume. Okay, and moreover, a series of examples. If you take any b and n, then this form that has only one real zero, which is simple, will also be generic. So these are just examples of forms on the boundary of the non-negativity form that have this generic behavior. And so why we call this such forms generic? Yes, please.
What is a simple zero?
So simple zero means that like from complex geometric point of view, it means that you have nodal singularity, and this literally means that the Hessian of the form at the zero has maximal possible n-1. Okay. So, and the motivation for calling these forms generic is because non-generic forms in the boundary, they form a semi-algebraic subset of codimension of least 2. And Bernd will say it has exactly 2, right? And which is moreover nowhere dense in the boundary. So non-generic forms are somewhat rare. They occur with probability 1 with respect to any natural measure on the boundary of the negativity there. Okay, and now I come to this question that I mentioned already. So now, unfortunately, genericity is only a sufficient condition for finiteness of the volume. And natural problem is to characterize at least those forms that have isolated real zeros and that have finite volume. Okay? For example, Motzkin does not have only simple zeros, but still it has a finite volume. And characterization, possible characterization can be, for example, in terms of singularity types of zeros of your form. Okay, and let me just explain why this boils down to a question about singularities. Because if you take a form that has only isolated zero, which is not always the case, because there are forms with infinitely many zeros, right? And assume just for simplicity that all its zeros lie in the affine chart. Okay, that is r to the n-1. And denote by y1, yk, all these zeros in the affine chart, that is zeros of this dehomogenized polynomial. then the volume is finite if and only if this integrals from here over arbitrary small neighborhoods of these real zeros converge. So the only thing that matters for finiteness of the volume is the behavior of the form around its zeros, right? As this picture shows it, right? So if you stay away from zeros, then nothing bad can happen. So infinite volume you can gain only around zeros. That's why you basically need to study conditions for the zero, for the isolated zero, so that this singularity is integrable with this exponent. Okay, I searched a lot in this singularity theory literature, but haven't found any such characterization. Maybe some further progress can be done for some classical singularities. Okay, now I go to second part of my talk. So I will talk about actually third part. I will talk about some property that you can study that kind of mimics Gaussian behavior, but has to do with high degree polynomials. So if you take n-dimensional centered Gaussian vector with covariance matrix sigma, then its density, probability density function, is given by this formula. Okay. So now the positive definite matrix sigma, which is known as a covariance matrix, consists of degree 2 moments of this probability density. So you can easily see that if you integrate products of variables against your density, against your Gaussian density, you will obtain the covariance matrix sigma. And it has a property that the inverse of the matrix Q that defines the quadratic in the argument of the exponent is essentially the inverse of the moment matrix of this probability distribution. Okay, so the all Gaussian distributions enjoy this property. So degree 2 moment matrix is inverse of the Gram matrix that defines the Gaussian. So we want to kind of mimic this property for high degree polynomials that are sums of squares. And this was already, I think Jean Bernard has already did that in 2012. So again, this m d half of y will denote the column vector of monomials of degree d half. Then you take any sum of squares that corresponds to Gram matrix G, and you define this exponential probability density function. Okay, this is exponential with the density of the exponential form associated with this sum of squares. And this k will just be a normalization constant, okay, to make things look nice. So for example, if d equals 2, you recover back your Gaussian density, because in this case k equals 2, one half, sorry. And you just get back your Gaussian density. And Jean Bernard in 2012 gave the following definition. So he called distributions with density Pg Gaussian-like if they enjoy similar property in terms of moments and the Gram matrix as Gaussian distribution would. So he called that Gaussian-like if this relation holds. So it means that your sum of squares form that you used to define the density function has one of the Gram matrices, one of its Gram matrices is the inverse of the moment matrix of this distribution. Okay. Yes.
Why do you need k here?
So k is just a normalization constant. As if I don't put k, some constant will pop up in this relation. Okay. So it's
Just
not.
to understand. So G is a very big matrix.
Yes.
This other one is small.
Which ones? Both are. So this lives in the same space.
Polynomials of high degree.
Yes.
There's a big
Exactly.
matrix. But we're talking about distributions on Rn. So it has a
The 2D moments.
Yeah, we take 2D
Oh,
moments.
I see.
We have the degree D moments of this distribution. Okay, so both matrices live in the same space. So let's say G is more or less the inverse of the moment matrix. But of course, there can be infinitely many G's, right? So
it's a tensor, moment tensor.
well, moment tensor. Yeah, tensor is a matrix is a tensor. No. Well,
The degree 2D, the moment of degree 2D is homogeneous polynomial.
so you take two.
The moment matrix which contains the moment of the degree 2D.
Think about bivariate case Hankel matrix.
You understand when high in dimension.
Yeah. Okay, but still, you take products of two monomials and integrate them. You can define moment tensors. This will be a separate story. Okay, so in words, the inverse of the moment matrix of this probability density function is a Gram matrix of the SOS form. Okay, and in the same work, Jean Bernard characterized when it happens that this Gaussian-like behavior occurs. Okay, so he proved that G is the inverse to the moment matrix associated to the sum of squares of G, if and only if G is a critical point of the following function. So if we take this function that associates each G, this case power of determinant times this mass of this exponential density, then this function, its critical points are exactly those G that correspond to Gaussian-like distributions. And this function is homogeneous of degree 0, and it happens thanks to the choice of the normalization K. And this K is this normalization that makes this function homogeneous of degree 0. And in the Gaussian case, by the way, this function will be constant. There will be nothing because every degree 2 sum of squares will be a Gaussian-like. That's the motivation. Yes, Greg.
So I just want to make sure that I understand. So you're saying you start with the sum of squares, right? You can have many Gram matrices,
exactly.
Right?
Exactly.
Now you pick Gram matrix according to this function.
Exactly.
Right. And then you're saying you take its inverse, and the inverse is going to end up being in the dual form.
Exactly. That's right. I will also copy that.
Okay.
Yes. So if you think about if you start with a bad choice, you can still get moment matrix that is inverse to the another Gram matrix. But this suggests you can. So here, this suggests that you start with the right choice already.
So following up, so this is a particular point in the ground spectrum?
Yes, it's a particular point.
It's like the best point.
The best point, exactly. So this result has a so this was characterization given by Jean Bernard, and beyond a trivial Gaussian case, no examples of Gaussian-like distributions were known. And the purpose of this talk is to give first examples in any degree in any number of variables. And these examples look quite silly. So you take sum of squares form, which is just power of the quadrant. Okay, you take the quadrant in small, corresponds to small matrix. Take the appropriate power of it. Then we prove that this has Gaussian-like behavior. That is, if you take so 1 Gram matrix of this power of the quadrant will be inverse of the moment matrix of this exponential-like Gaussian probability distribution. Is the result clear? Yeah. So, an equivalent formulation of this result, if you don't like to talk about sums of squares and exponential densities corresponding to high degree polynomials, you can formulate this result entirely in terms of Gaussians. You can take, now you consider another class of densities, which is just Gaussian densities corresponding to the covariance matrix 2 inverse that have certain normalization, extra covariance normalization, okay, which is also like not important to state the result, but just makes things nicer. So again, if d equals 2, this extra normalization constant sigma d will be 1, and this will be just the classical Gaussian density with covariance matrix 2 inverse. And that's an equivalent formulation of our result. Degree d moments of the Gaussian measure satisfies this relation. Okay, so this can be viewed as a sequence of relations that moments of high order moments of Gaussian have to satisfy. So you take the quadratic form, you take any d here, you compute this moment matrix, and then these moments have to match the coefficients of this power in the quadratic form. Okay, and again now because I'm coming back to questions that Greg and Baron posed. So you take the dual cone to PSD cone, that is so-called pseudo-moment cone. And this cone is isomorphic to the PSD cone of Hankel type pseudo-moment matrices, right? So if you take linear functional L that evaluates to non-negative things on the sum of squares cone, then you can associate with the matrix of degree d moments just by this formula, right? And if L comes from a measure that is, it's a moment functional, right? Then this matrix MD of L will be filled with moments of this associated measure of degree D, right? So that's why it's called pseudo moments and moments. And Nesterov gave a beautiful characterization, a beautiful duality between interiors of the SOS cone and its dual that looks as follows. So if a form G is in the interior of the sum of squares cone, if and only if there exists a unique, actually L, unique moment functional, pseudo moment functional in the interior of the pseudo moment cone, so that one of the gram matrices of the SOS form G is the inverse of the pseudo moment matrix. Okay, that's it. Yes.
Excuse me. The dual cone is essentially the envelope of the Veronese, the convex envelope of the Veronese.
That happens for the dual to the non-negativity cone. This is something larger.
This is
Yeah.
so it is the dual of
Sum of squares sit inside positive non-negative polynomials, and if you dualize the moment cone, which is the convex hull of the Veronese, will be smaller in this pseudo moment cone, right?
okay.
So this is a Nesterov characterization, and as I said, this moment function, pseudo moment function L is unique with this property. So it's a unique, this best gram matrix. And the remark, L form, that is the power of quadric, is self-dual in the sense that it has gram matrix actually, which corresponds to actually moment functional, not pseudo moment, but moment functional associated with the Gaussian density, or equivalently, if you think of it still in these terms of Gaussian-like distribution, then this moment, this gram matrix is the inverse of the moment matrix. So that's a natural question: is to characterize other forms in the interior of the SOS cone that have the same property, right? So what was a Nesterov so characterize self-dual SOS forms in the interior that have similar behavior. So that would be another nice question. Okay.
Nesterov is currently very only for this type of form, or
No, it holds in more general situation. I think it's he takes any collection of functions, I don't know, trigonometric polynomials, whatever, systems of they have to be kind of behave similar to this. Yes, correct.
But I mean, the natural context to make it more general to just say I don't know if it works, but you just take projections of the cone of PSD matrix, right? I mean, this SOS cone is some projection of a cone of PSD matrix.
Yes, yes.
Right? And then dual cone, so everything.
Yeah, exactly.
The terminology makes sense. Maybe you make sure that the projection is nice.
Yeah, exactly. So that's.
And does it work? Is there?
In this setting, I don't know. I know that it works when set class of functions you deal with is a span of products of kind of monomials. So, but we can talk later. Right. So again, now I just want to give some ideas of proof. So I still have, I think. Oh, no, I don't have much time. I have maybe 5 minutes, right? Is that so? So how do we prove this result? So first of all, let me point out that it's convenient to work with a vector of normalized homogeneous monomials, because in that case things get particularly nice, because this normalized monomials, they form an orthonormal basis of the space of homogeneous polynomials with respect to the Bombieri inner product, right? And another nice property of Bombieri inner product is that it's invariant with respect to orthogonal transformations, right? That means that if I transform the vector of normalized monomial by some orthogonal transformations, this amounts to applying big orthogonal matrix to the vector of normalized monomials at point x, right? This is just representation theory of the orthogonal group. Okay, and moment matrix with respect to the normalized monomials satisfies the following nice property. So it's not important whether we work with moments or with normalized moments or with monomials or normalized monomials. These forms will be will be the same. it's not important which definition we use, whether with hats or without hats. And that gives us advantage that we can use this orthogonal invariance to first diagonalize our quadratic, okay, to come to the diagonal situation. And so first it remains to prove the things for diagonal case, because then we can apply back orthogonal transformations to go to the general case. And furthermore, if we take diagonal matrix, we know that it has to be PSD, so its eigenvalues have to be squares of some other positive numbers. Then the next relation holds. So this degree SOS form will be equal to this SOS form. So where in the middle, there is inverse of the moment matrix associated to the identity matrix. And argument of this vector of moments are just Hadamard product of X with the square root of this vector of eigenvalues of our diagonal matrix. And this allows to make us further reduction. And our goal will be equivalent to proven things just for that diagonal case. Can go completely to the, sorry, not to the identity, for the identity. It's even more simple, okay? So it remains to prove this relation for the identity, namely for the standard Gaussian distribution. So we just need to prove that this form on the left is the power of sums of squares of the variables. Okay. And in order to prove that, there are two things to show. First of all, one needs to show that this form on the left is invariant with respect to ON. And second, in order to find concept of proportionality, it suffices to integrate both sides against the measure, and then you will see that the constant is one. Okay, in summary, so I'm done with proof ideas. And so what we did, we established complete monotonicity of the volume function and characterized forms, partially characterized forms with a finite volume, and discovered a series of examples of Gaussian-like distributions. And some questions that I already mentioned. So one question is to characterize forms that have finite Lebesgue volume. And furthermore, find more Gaussian-like SOS forms rather beyond this one. Okay, and you can find out more in our preprint. And thanks a lot for your attention.
We have a question there.
So in the finite volume question, so there's a concept of real log canonical threshold.
I have no idea what it is.
Okay, so there's a complex analytic theory of log canonical thresholds, but here you want the real version.
Okay.
This has also been used in learning theory.
Okay, we'll talk about it.
So Lorenzo has a question.
Yes.
I have a computational question. Did you try to apply in practice some of the formulas that you find with the volumes and compare them to other people?
No. Well, I think Jean Bernard did some works already on computation of algorithm.
It's a computing the partition function is very difficult actually. Explanation of homogeneous polynomial integrated without no space. No, it's not easy.
But you have another work where you have this.
We can do approximation and generalize.
Yeah.
There was a very nice work by Russian people who tried to find the algebraic characterization that you had with the determinant, but they could do it only in very few cases.
Right.
Those integral apparently appear in physics.
Right.
They call that discriminant integrals.
Yeah, exactly.
Yeah,
So this explicit expression for the volume in the quadratic case, which is a power of determining, if you ask the same like for higher degree, then but because of SLN invariance of the problem, you essentially forced to write the expression in terms of invariance of the action, SLN action on the space of forms. And then there are some hypergeometric type expressions obtained by physicists in the physics context for this type of function, but they don't care about non-negativity. They do it analytically. So yes.
When you consider some of Gaussian,
Some of that, like mixtures. Mixtures of Gaussian. Well, whether like, and then you, well, we haven't thought about it, but it's natural, it would be natural question to ask.
So the
Yes.
last question
Ah.
by Lorenz,
Ah.
sorry.
I want to ask you to try to generalize from the polynomial ring to coordinate field of some real variety.
Yeah.
Maybe easier you find another.
Yeah, yes, I wouldn't expect that there is like easy generalization, but maybe something can be said.
Okay, so the very last question by.
Can you extend to density which are not only with the homogeneous polynomials, homogeneous moments, but all moments?
Well, depends how you are. So we exploit homogeneity heavily in order to things. But if you modify the context a little bit, then I think it would be just equivalent to our setting, but you would need to restate things. Okay.
All right, so we stop here. I suggest we start again at 11:10, so that we have a good break and because Francis has a lot of questions.
Thanks, man.